The universe once forgot how to be a universe. We treat the laws of physics as unchanging commandments, but they may have been torn up and rewritten. This is the story of how physics broke down and reality rebuilt itself from the ashes. By the end, you will see the cosmos not as a static clockwork, but as a living, breathing entity capable of profound change. We will venture to the edge of a black hole where time stops, and into the primordial fire where all rules were born. What does it mean to live in a reality that is still under construction? Our world is built on a foundation of predictable rhythms. An apple falls from a tree, planets trace perfect ellipses around the sun, and light travels at a constant, unbreakable speed. For centuries, this cosmic order felt like an unshakable truth. Isaac Newton gave us the mathematics to describe the force of gravity, and Albert Einstein later reshaped our understanding of space and time itself, weaving them into a single fabric. This elegant framework made the universe feel like a grand, predictable machine, a clockwork cosmos whose gears we were slowly learning to map. Scientists like Carl Scham celebrated the beauty and power of these laws, seeing in them a profound connection between human reason and the workings of the cosmos. Yet this comforting order is an illusion, a temporary state of calm in a much more turbulent and chaotic reality. The first cracks in this facade appeared not in the vastness of space, but in the bewildering realm of the very small. Quantum mechanics revealed a subatomic world where particles can be in two places at once, where chance, not certainty, governs their behavior, and where simply observing something can change its nature. This is not the predictable universe of Newton and Einstein. What if the stable laws we rely on are not eternal commandments, but merely the current settings, a phase the universe is passing through? This unsettling question pulls back the curtain on a deeper mystery, pointing us toward a time when all known physics ceased to function, and reality had to start over from nothing. Our current laws of physics do not just bend at the edges, they shatter completely when we rewind time to the very beginning. The Big Bang was not an explosion in space, but the violent emergence of space and time themselves from a state of infinite density and temperature. In that first fleeting moment, the universe was a searing forge where energies were so immense that the four fundamental forces we know today, gravity, electromagnetism, and the strong and weak nuclear forces, were fused into a single, unified power. Particles as we understand them did not exist. Matter and energy were interchangeable in a primordial soup where the very concepts of here and there, before and after, lost all meaning. This is the singularity, a point where the mathematics of Einstein and the rules of quantum mechanics both fail, offering no answers, only profound questions. Physicists like Stephen Hawking probed this boundary, suggesting that in this initial fire, the universe operated under a completely different and now forgotten set of laws. The evidence for this cosmic amnesia is written into the fabric of our reality today. We see it in two great puzzles, the horizon problem and the flatness problem. The horizon problem asks why the universe looks so uniform. If you look at the cosmic microwave background, the leftover heat from the Big Bang, the temperature is the same in every direction you point your telescope. But according to the Standard Model, these distant regions of space should never have been in contact with each other. There simply has not been enough time since the beginning for light or heat to travel between them and even out the temperature. It is as if you walked into a room and found 1,000 people who had never met all wearing the exact same outfit. How could such perfect coordination be possible? The flatness problem is just as strange. The The geometry of our universe is incredibly, precisely flat, meaning parallel lines will never meet or diverge. For the universe to be this flat after nearly 14 billion years of expansion, its initial conditions at the Big Bang had to be fine-tuned to an accuracy of 1 part in 10 to the power of 60. That is a number so unimaginably precise it is like balancing a pencil on its tip for billions of years, a feat of impossible stability. These are not minor quirks, they are fundamental anomalies that point to a breakdown of our standard story. The leading solution to these riddles is a concept called cosmic inflation. The theory proposes that a fraction of a second after the beginning, the universe underwent a period of hyper-accelerated expansion, inflating from smaller than a proton to a vast volume in an unimaginably short time. This explosive growth would have stretched any initial wrinkles in space-time perfectly smooth, solving the horizon problem, and it would have forced the geometry of the universe toward flatness, solving the flatness problem. But inflation itself is a symptom of the deeper truth that the early universe was governed by a different physics. It was a phase transition, a moment when the unified force broke apart and the distinct laws we know today began to crystallize as the cosmos cooled. This means the predictable rules we rely on were not the starting point, they were the outcome. The seeds of cosmic forgetfulness were planted in that first violent second, a period of such extreme physics that reality had no choice but to adapt and rewrite its own operating manual, setting the stage for the quantum weirdness that would later emerge from the shadows. This quantum weirdness does not stay confined to the tiny world of atoms. It bleeds into the very structure of reality, challenging our most basic assumption that every effect must have a cause. In our everyday lives, causality is the backbone of existence. You throw a ball, it breaks a window. The throw causes the break, but in the quantum realm, this tidy chain of events dissolves into a fog of probability. Particles can be linked across vast distances in a phenomenon called entanglement, where measuring the spin of one particle instantly determines the spin of its partner, no matter if they are light years apart. There is no signal traveling between them, no communication that could explain the coordination. It is as if two coins, flipped on opposite sides of the galaxy, always land on the same face, defying any notion of local cause and effect. This spooky action at a distance, as Einstein called it, suggests that at a fundamental level, the universe is deeply interconnected in ways that violate our classical logic. The act of observation itself becomes a cause that creates an effect, forcing a particle to choose a definite state from a cloud of possibilities. This was the core of the famous debate between Niels Bohr and Albert Einstein, with Bohr arguing that reality is not deterministic but probabilistic, its very nature dependent on how we look at it. To illustrate just how strange this is, Erwin Schrödinger proposed his famous cat thought experiment. A cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers and the poison is released. But according to quantum rules, the atom exists in a superposition. It has both decayed and not decayed until someone opens the box and looks. This means the cat, by extension, is both alive and dead, a ghostly mixture of states until the observation collapses the probability wave into a single outcome. The very act of looking seems to write reality into existence. Experiments like the double slit demonstrate this profound weirdness with startling clarity. When you fire particles like electrons at a barrier with two slits, they do not behave like tiny bullets going through one hole or the other. Instead, they behave like waves passing through both slits at once and creating an interference pattern on the screen behind them. But if you place a detector to see which slit each electron actually goes through, the interference pattern vanishes. The electrons now being watched behave like well-behaved particles. Your simple decision to observe changes the outcome of the experiment. This leads to radical interpretations like the many worlds theory, which suggests that every possible outcome of a quantum event does actually happen, but in a separate, branching universe. Every time the cat is both alive and dead, the universe splits, creating one reality where it lives and another where it dies. If this is true, then our linear experience of cause and effect is just a single thread in an infinite tapestry of parallel realities. Underpinning all of this is Werner Heisenberg's uncertainty principle, which places a fundamental limit on what we can know. You cannot simultaneously know a particle's exact position and its exact momentum. The more you pin down one, the more the other becomes a blur. This is not a limitation of our measuring devices, it is a built-in feature of reality. The universe at its heart is not a collection of definite things, but a sea of probabilities and potentialities. So what does this mean for our understanding of time? If cause and effect can be reversed or entangled, if the present can rewrite the past through quantum retrocausality, then our arrow of time may be nothing more than a compelling illusion, a story we tell ourselves in a cosmos where every possible history is still in play. We treat the flow of time from past to future as an unbreakable rule, the one constant in a changing universe. Yet this arrow of time is not an absolute law of physics, but a mystery born from the specific conditions of our cosmos. The fundamental equations that describe reality, from Newton's mechanics to Einstein's relativity, work perfectly well if time runs forward or backward. There is no mathematical reason why an egg cannot unbreak, or why smoke cannot pour back into a cigarette. The one-way direction we experience seems to come from a single, profound concept, entropy, which is the measure of disorder in a system. The second law of thermodynamics states that the total entropy of the universe always increases. Things move from order to chaos, and this gives us our past and our future. But could this law ever be suspended? Could time itself stumble or even run backward? General relativity provides theoretical playgrounds where this might be possible. In the warped space-time around a rotating black hole, solutions to Einstein's equations allow for closed time-like curves. These are paths through the fabric of the cosmos that could, in theory, loop back on themselves, allowing a traveler to return to their own past. Wormholes, hypothetical tunnels through space-time, could act as bridges not just between distant points in space, but between different moments in time. Physicist Kip Thorne explored these ideas rigorously, showing that while they may require exotic matter to remain stable, they are not forbidden by our current understanding. On a quantum level, we already see hints of time's strange flexibility. Certain subatomic interactions, like those involving kaon particles, appear to be symmetric in time. The equations governing their behavior look almost the same whether time flows forward or backward, suggesting that at the most fundamental level, the universe does not strongly prefer one direction over the other. So what gives us our persistent arrow of time? The leading idea is that the Big Bang created a universe in a state of incredibly low entropy and state of exquisite order. Everything since has been the long, slow unraveling of that order into the chaos we see today. Our experience of time is just us riding that wave of increasing disorder. But if that is true, then in a different part of the multiverse, or in the aftermath of some cosmic upheaval, the initial conditions could have been reversed. A universe could have begun in a state of high entropy and be moving toward order, making its inhabitants perceive time as flowing backward relative to us. Their broken eggs would spontaneously reassemble, and they would remember the future while anticipating the past. These are not just wild speculations, they are challenges to our deepest assumptions about causality. If time can loop, then an effect could become its own cause. A person could go back in time and by accident prevent their own birth. The very logic that holds our reality together would begin to fray at the edges. This brings us to the ultimate cosmic rule breakers, where time does not just bend, but where its very meaning is erased, the singularities at the heart of black holes. At the edge of a black hole, the universe forgets its own name. Here, gravity has won a total victory, crushing matter into a point of such infinite density that space and time themselves are torn apart. The boundary of this cosmic abyss is the event horizon, a point of no return from which not even light can escape. Crossing this threshold is not like falling into a dark pit. It is like rowing a boat toward a waterfall that has no bottom. Once you pass the lip, every possible path leads inward toward the center. There, according to the mathematics of general relativity, lies the singularity, a place where density and curvature become infinite, and our reliable equations simply output error messages. Physicist Roger Penrose described these regions as the points where Einstein's theory breaks down, where the predictable fabric of causality we rely on is shredded. But the strangeness does not stop at the edge. In the 1970s, Stephen Hawking made a startling calculation. He realized that black holes are not completely black. Due to bizarre quantum effects occurring just outside the event horizon, they slowly leak radiation and evaporate over astronomical timescales. This Hawking radiation presents a profound paradox. According to quantum mechanics, information can never be truly destroyed. If you burn a book, every single letter and word is, in principle, recoverable from the smoke and ashes. But if a black hole evaporates entirely, what happens to all the information about the stars, planets, and atoms that fell in? It seems to vanish forever, violating a fundamental quantum law. This is the black hole information paradox, a direct conflict between the rules of gravity and the rules of the quantum world. Real-world observations are now bringing these theoretical nightmares into focus. The Event Horizon Telescope captured the first ever image of a black hole, a fiery ring of light surrounding a perfect shadow of darkness. That shadow is the event horizon, a real place in our universe where gravity is so strong it traps light itself. This confirms we are not just dealing with mathematical abstractions, but with actual regions where physics as we know it ceases to function. So what truly happens to the information that crosses the threshold? Some theories suggest it is scrambled and radiated back out in a form we cannot decode. Others propose it is stored on the surface of the event horizon, a holographic record of everything consumed. The most radical idea is that the information is sent to another universe or is lost forever, forcing our reality to rewrite its most basic conservation laws to accommodate the void. This confrontation at the edge of a black hole points to an even deeper layer of cosmic rule breaking hidden in the empty space all around us. The void itself is rebelling. We think of empty space as a true nothing, a silent and static stage upon which the cosmic drama plays out. But quantum physics paints a far more unsettling picture. The vacuum of space is not empty at all. It is a seething, bubbling sea of virtual particles that constantly flicker in and out of existence. This quantum foam possesses a real, measurable energy, a background hum to the cosmos known as vacuum energy. And according to our best theories, this energy should be immense. When physicists calculate the predicted strength of this vacuum energy using quantum field theory, they arrive at a number of such staggering magnitude that it defies comprehension. Then they look out at the real universe. By measuring the rate of cosmic expansion using distant supernova, astronomers like Adam Rees discovered that the universe is not just expanding, but its expansion is accelerating, driven by a mysterious force we call dark energy. The measured strength of this dark energy, which acts like the energy of the vacuum, is not just a little bit off from the theoretical prediction. It is wrong by a factor of 1 followed by 120 zeros. This is not a small rounding error. It is the largest discrepancy between theory and observation in the entire history of science. This is the vacuum catastrophe, a clear signal that something fundamental in our understanding is broken. The cosmological constant problem lies at the heart of this crisis. Einstein originally introduced a cosmological constant into his equations to represent a repulsive energy in the vacuum that would keep the universe static. He later called it his greatest blunder, but modern cosmology has brought it back. The problem is one of balance, or rather, a catastrophic lack of it. The vacuum energy predicted by quantum mechanics should be so powerfully repulsive that it would have ripped the universe apart in the first fraction of a second, preventing stars, galaxies, or life from ever forming. Yet our universe is here, and its acceleration, while real, is far gentler and more recent. How can the energy of nothing be so potent in theory, yet so subtle in reality? The data from observing supernova acts as a cosmic speedometer. By studying how the light from these exploding stars stretches and dims over vast distances, we can chart the expansion history of the universe. The results are unequivocal. About 5 billion years ago, the expansion of the cosmos began to speed up, as if an invisible foot was pressed on the accelerator. This dark energy now dominates the cosmos, but its measured value is that impossibly tiny number. Why is the universe so much quieter than our math says it should be? Could this be a sign that the physical constants we take for granted are not truly constant, but are instead frozen remnants of a more chaotic past? One radical solution to this puzzle is the multiverse. If our universe is just one bubble in an infinite froth of universes, each with different laws and physical constants, then we simply live in one where the vacuum energy is, by sheer chance, small enough to allow for our existence. In most other universes, the energy was too high or too low, and those cosmos flamed out or collapsed instantly. Our stable reality, then, would not be the product of fine-tuned laws, but the result of a cosmic lottery we happen to win. This energy imbalance, this vacuum catastrophe, might be more than just a calculation error. It could be a fossil, a relic of a time when the rules of reality were not yet set in stone, pointing toward a cosmos where the very constants of nature can be rewritten. Our own universe might be a single page in an infinite cosmic library. The multiverse hypothesis suggests that our reality, with its specific laws and constants, is not unique. It is just one possibility in a vast, perhaps endless, collection of parallel universes. This idea does not come from science fiction, but emerges naturally from our most ambitious scientific theories, like cosmic inflation and string theory. The same inflationary process that smoothed our early cosmos could be eternal, continually spawning new universe bubbles in a frothing sea of reality. Each of these bubbles could have its own unique physics, a different set of fundamental rules. In one universe, gravity might be so strong that stars burn out in 1,000,000 years. In another, the nuclear forces might be too weak to bind atoms together, preventing chemistry and life from ever beginning. Physicist Max Tegmark categorizes these levels of the multiverse, from universes just beyond our cosmic horizon to realms with entirely different dimensions and physical laws. This leads directly to a profound question. Why do the rules of our universe seem so perfectly tailored for our existence, the answer might be the anthropic principle. It simply states that we can only observe a universe capable of producing observers like us. In the unimaginably vast landscape of all possible universes, most are sterile and empty, with constants too hostile for any complex structure to form. We do not live in a special universe, we simply live in one of the rare habitable ones. A stark thought experiment called quantum suicide illustrates this. Imagine a device that, based on a quantum event, has a 50% chance of killing you every time you press a button. From your perspective, you would keep pressing the button and, against all odds, always survive. In the many worlds interpretation, you are simply the version of yourself who continues to exist in the branch of the multiverse where the gun never fires, while countless other versions of you in parallel realities perish. This is a disturbing but logical consequence of the theory. Our continued existence filters our perception of reality. So, is our cosmos a unique creation or just one address in a sprawling multiverse? The answer rewrites our place in the cosmos, suggesting that the very laws we rely on were not designed, but randomly selected, setting the stage for the final and most profound rewrite of all, the moment of cosmic genesis itself. The universe solved its own problems with a single, breathtaking rewrite. In the first sliver of a second after the Big Bang, a mysterious force field, dubbed the inflaton field, switched on. This was not a gentle expansion. It was a hyper-accelerated stretching of space itself, a period known as cosmic inflation where the universe doubled in size over and over again, faster than the speed of light. This was not matter moving through space faster than light, which is forbidden, but space itself stretching, a loophole in the rules that allowed reality to balloon from smaller than a proton to the size of a grapefruit in a time span so short it has no comparison in human experience. Theorist Alan Guth proposed this idea, realizing it elegantly solved the great puzzles we face. The horizon problem vanished because the entire observable universe was once a tiny, connected speck that had ample time to even out its temperature before inflation blew it apart. The flatness problem was also resolved, as inflation would have stretched the fabric of space so taut that any initial curvature would have been smoothed into the precise flat geometry we measure today. But this cosmic fix came with a profound implication. The physics driving this event, the inflaton field and its energy, does not correspond to anything in our current standard model. It represents a different set of laws, a phase of reality where the rules were temporarily different to create the stable universe we inherited. As this field decayed, its immense energy flooded the cosmos, reheating it into the hot soup of particles that would eventually form atoms, stars, and us. The most stunning evidence for this great rewrite is etched into the oldest light we can see. The cosmic microwave background radiation is not perfectly smooth. It contains tiny, whisper-quiet variations in temperature, a mottled pattern across the sky. These are the fossilized seeds of all future structure. During inflation, minuscule quantum fluctuations, the inherent jitter of the inflaton field, were stretched from the subatomic scale to cosmic proportions. Those tiny ripples in energy became the gravitational wells where matter would later coalesce, forming the vast cosmic web of galaxies and voids we see today. Our entire cosmic architecture, from the Milky Way to the most distant quasar, began as a quantum tremor amplified by inflation. So did this process simply follow a deeper, unknown law? Or was it a genuine moment of cosmic rule breaking, a necessary reboot to create a universe capable of complexity and life? This forces us to confront an even more unsettling possibility. If the fundamental forces themselves were forged in the fire of the early universe, could other constants, even the speed of light itself, be mere artifacts of that primordial transition? The bedrock of reality may be shifting beneath our feet. We build our understanding of the cosmos on fundamental constants, numbers like the speed of light in a vacuum or the charge of an electron, believing them to be the same yesterday, today, and forever. But what if they are not? The variable constants hypothesis dares to suggest that these pillars of physics might have been different in the distant past, changing as the universe cooled and its laws settled into their current form. This is not a minor adjustment, it is a complete rethinking of cosmic stability. Astronomer John Webb and his team analyzed the light from incredibly distant quasars, the brilliant cores of ancient galaxies. As this light traveled for billions of years, it passed through clouds of interstellar gas which absorbed specific wavelengths, leaving a fingerprint in the spectrum. Webb's astonishing finding was that the patterns of absorption suggested a tiny but statistically significant difference in the value of the fine structure constant. This number, often called alpha, governs the strength of the electromagnetic force. In the early universe, it appears to have been slightly smaller. A different alpha means a different universe. The electromagnetic force dictates how atoms bind together, how chemical reactions proceed, and how stars burn. If alpha were larger, atomic nuclei would repel each other more strongly, making it harder for stars to fuse hydrogen into helium. The serene glow of stellar nurseries could be replaced by a darker, quieter cosmos. A smaller alpha, as the data hints, would have subtly altered the nuclear processes inside the first stars, potentially changing the recipe for the elements that make up our very bodies. This idea extends beyond electromagnetism. Could the strong nuclear force which glues protons and neutrons together have been stronger in the primordial fire? If so, the formation of the first atomic nuclei in the aftermath of the Big Bang, a process known as Big Bang nucleosynthesis, would have produced a different mix of hydrogen and helium, rewriting the universe's elemental fuel from the very start. This leads to even more radical proposals like varying speed of light theories. What if the ultimate cosmic speed limit, the constant c in Einstein's famous equation, was not always the same? In the first frantic moments, a faster speed of light could have allowed the distant parts of the cosmos to communicate, solving the horizon problem without the need for inflation, or perhaps as part of a different kind of inflationary epoch governed by unfamiliar rules. The implications are staggering. If the constants are not fixed, then the laws of physics are not so much discovered as they are local and temporary. The universe could be evolving, with its fundamental parameters slowly changing over cosmic time. We are left to wonder, are the numbers we measure simply the ones that happen to be in effect during this current cosmic era, in this particular corner of existence? This search for shifting foundations brings us face to face with a deeper principle, the role of symmetry in holding the entire cosmic edifice together. Symmetry is the silent architect of our universe, a hidden order that dictates how particles interact and forces behave. But this perfect balance was not always destined to last. In the earliest, hottest moments, the cosmos was a place of supreme symmetry, where the forces we now see as distinct were fused into one. The electromagnetic force and the weak nuclear force were a single, unified power. There was no difference between them. As the universe expanded and cooled, it crossed a critical threshold. This was the electroweak phase transition, a moment when the universe forgot its perfect balance. The single, symmetric force broke apart, giving birth to the two separate forces we recognize today. Think of it like a ball balanced perfectly at the very top of a hill. This is the symmetric state, unstable and temporary. The slightest nudge, a drop in temperature, sends the ball rolling down into one of the valleys below. The symmetry is broken. The ball has chosen a specific state, and it can never return to that perfect, precarious point at the top. In the cosmos, this rolling ball was the Higgs field, a fundamental energy field that permeates all of space. Before the break, particles like electrons and quarks raced through this field at the speed of light, utterly massless. But as the Higgs field settled into its new, stable state, it began to interact with these particles, dragging on them and giving them the property we experience as mass. This is the Higgs mechanism, an idea championed by physicists like Peter Higgs, which explains why some particles are heavy while others, like photons, remain weightless. Without this cosmic forgetfulness, this breaking of symmetry, there would be no atoms, no chemistry, and no us. The universe would be a sea of massless particles forever flying apart at light speed. But this rewriting of the rules was not always clean. When a symmetric state breaks, it can leave behind cosmic scars. Just as freezing water can trap air bubbles in ice, the rapidly cooling universe could have trapped regions where the old, symmetric physics was locked in place. These could manifest as cosmic defects like magnetic monopoles, theoretical particles that are a single, isolated north or south magnetic pole, unlike any magnet we have ever seen. Their existence would be a direct fossil of that primordial imbalance. Could this have happened more than once? Were there other, even grander symmetries that broke in the first instance, each one dramatically altering the operating system of reality and forging the laws we now take for granted? This process of cosmic transformation, of the universe shifting from one phase to another, suggests that our entire existence is built upon a series of forgotten rules. These cosmic symmetry breaks were not gentle shifts but violent upheavals. The early universe underwent a series of dramatic phase transitions, moments when the entire cosmos changed its state as abruptly as water freezing into ice. Each transition rewrote the operating rules of reality, locking in new laws that would govern the future. One of the most pivotal was the QCD transition. In the first microseconds, the universe was too hot for nuclear matter to form. It was a perfect, searing plasma of free quarks and gluons, the fundamental building blocks that had not yet been locked away. Then, as the cosmos expanded and cooled past a critical temperature of trillions of degrees, a profound shift occurred. The strong nuclear force suddenly became dominant, and those free-floating quarks were forced to condense, binding together in groups of 3 to form the first protons and neutrons. It was a cosmic imprisonment, creating the very nuclei that would one day build every atom in your body. This was not a smooth process. Theorists like Edward Witten suggest that such a violent change in the state of the universe's fundamental material would have sent powerful ripples through the fabric of space-time itself. These primordial gravitational waves would be a faint echo of that moment, a direct signal from the instant matter as we know it was forged. The physics of this transition is governed by thermodynamics, by the search for stability. Just as supercooled water will suddenly crystallize when a speck of dust disturbs it, the quark-gluon plasma became unstable as it crossed that critical temperature threshold. It had to find a new, more stable arrangement, and in doing so, it released immense energy and potentially created cosmic defects that could have acted as seeds for the very first structures. Could the vast web of galaxies we see today have been imprinted by the turbulent aftermath of this quark confinement? This leads to a deeper, more unsettling thought. Are these cosmic phase transitions a finished chapter of our history, or could they happen again? The vacuum of space itself may not be in its most stable state. What we perceive as empty space could be a false vacuum, a temporarily stable valley in a much larger cosmic landscape. A random quantum event could, in theory, trigger a new phase transition, a bubble of true vacuum that expands at the speed of light, rewriting all the laws of physics in its wake. The rules we depend on could be far more fragile than we ever believed. our universe could be resting on a fragile foundation, a temporary state of peace before an inevitable collapse. This is the concept of the false vacuum, a deceptively stable arrangement of empty space that might not be the most stable one possible. Think of it like a ball sitting in a small, shallow valley on the side of a massive mountain. The ball seems stable for now, but there is a much deeper valley far below. All it would take is a small nudge, a random quantum fluctuation, for the ball to roll out of its shallow dip and tumble all the way down, releasing a colossal amount of energy as it falls. In cosmic terms, that shallow valley is our current vacuum, the set of physical laws and constants that define our reality. The deeper valley represents the true vacuum, a state with entirely different, and for us, completely unknown physics. The work of theorists like Sidney Coleman paints a terrifying picture of how this transition, called false vacuum decay, would unfold. Somewhere in the cosmos, a single, random quantum event could nucleate a bubble of true vacuum. This bubble would not expand like an explosion of matter, but as a sphere of redefined physics, its wall rushing outward at the speed of light. Inside this expanding frontier, the fundamental laws would be rewritten. The strength of gravity, the nature of atoms, the speed of light itself, all of it would be replaced. There would be no warning. One moment, the universe as we know it exists. The next, a wall of absolute transformation sweeps through, erasing galaxies, stars, and life itself, not with fire and force, but by redefining the very concept of what matter and energy are. The cosmos would undergo the ultimate reset. Could such an event happen spontaneously? The probability is astronomically low on any human timescale, but given the vastness of space and time, it remains a haunting possibility. This forces a profound reflection. Is our entire existence, from the grandest galaxy to the most delicate thought, entirely dependent on a single, precarious quantum state? The information that defines our reality, every memory and every law of physics, would be lost not to destruction, but to irrelevance, erased in a new cosmic order where such concepts may no longer have any meaning. In this light, the slow rise of entropy we experience might just be a temporary symptom of our unstable vacuum, a fleeting pattern in a cosmos forever teetering on the edge of its own reinvention. The universe is slowly forgetting. Every moment, as entropy increases, the cosmos loses a little more detail, moving from a state of sharp, specific memory into a blurry, disordered haze. This is the second law of thermodynamics in action, the relentless drive toward chaos that gives us our arrow of time. But what happens when this process does not just blur the details, but erases the entire cosmic ledger? This is the terrifying possibility that emerges when physics breaks down, a true cosmic amnesia where the universe forgets its own past. Nowhere is this threat more stark than in the black hole information paradox. We think of information as abstract, but it is the most concrete thing there is. It is the precise arrangement of atoms that makes a star, the unique sequence of genes that defines a life form, the specific spin of every electron that fell into a black hole. Quantum mechanics insists this information is never destroyed, only scrambled. Burn a book, and in theory, you could reconstruct every word from the smoke and ashes. But a black hole that evaporates via Hawking radiation seems to present a receipt for total annihilation. The information about whatever fell in appears to be permanently lost, violating a core quantum rule. This paradox pits our two most successful theories, general relativity and quantum mechanics, against each other in a fight for the soul of reality. One proposed solution is as radical as the problem itself, the holographic principle. Physicist Leonard Susskind and others suggest that all the information describing a three-dimensional volume of space can be encoded on its two-dimensional boundary, like a cosmic DVD. The event horizon of a black hole would therefore hold a perfect, scrambled record of everything that ever crossed it, a holographic film stored on the surface of the void. When the black hole evaporates, this information is theoretically radiated back out, preserving the cosmic ledger. But what if, in the singularity at the center, the breakdown is so complete that this fails? What if the hologram is burned and the information is truly deleted from existence? This would be the ultimate rule change, a point where the universe does not just move toward disorder, but actively forgets its own history. In our everyday world, entropy's increase is a one-way street. Yet in the quantum realm, we find strange loopholes. Quantum computers rely on maintaining coherence, a state where bits of information, or qubits, can exist in multiple states at once. This is a state of low entropy and high information. For the computer to function, this delicate coherence must be protected from the disruptive noise of the environment, a process called decoherence that rapidly increases entropy and destroys the calculation. In lab experiments, scientists fight this natural tendency toward disorder, creating isolated pockets where quantum memory is preserved against the universal tide. These tiny, controlled environments show us that the relationship between information and disorder is not always straightforward. Could the entire early universe have been in such a coherent, low-entropy state, a cosmic quantum computer whose eventual decoherence wrote the first laws of physics into being? The increasing disorder of the cosmos might not just be a passive fading, but an active engine for change. Each major phase transition, from the breaking of the electroweak symmetry to the confinement of quarks, was a massive leap in entropy, a dramatic reshuffling of the cosmic deck. With each shuffle, the old rules became obsolete, and new ones crystallized from the chaos. Is our stable reality simply the current, temporary equilibrium in an endless series of cosmic reorganizations? If the universe can forget the specific arrangement of a star, could it also forget the laws that made that star possible? This leads to a deeply personal question. How does our own consciousness, a process seemingly dependent on the orderly flow of information in our brains, perceive a reality whose foundational rules might be so transient? Are we, in our struggle to remember and understand, simply mirroring the cosmos' own fragile fight against forgetting? Our own consciousness may be the final piece in this cosmic puzzle. If the laws of physics were rewritten during the universe's turbulent birth, who was there to witness the change? This leads to a profound philosophical question. Does reality exist independently, or is it somehow shaped by the act of observation itself? The most mainstream interpretation of quantum mechanics, the Copenhagen interpretation, places the observer at the very center of the story. It suggests that a particle exists in a blurry cloud of potential, a superposition of all possible states, until a conscious mind measures it. At that moment, the wave function collapses and a single, definite reality snaps into focus. In this view, consciousness is not a passive spectator, but an active participant that forces the universe to make up its mind. The physicist John Wheeler took this idea even further with his concept of the participatory universe. He proposed that we live in a cosmos that only comes into existence through the act of observation. In a sense, the universe is building itself backward from the future, with our present measurements determining its past. His famous delayed choice experiment illustrates this stunning possibility. Imagine a particle of light, a photon, traveling through a maze of mirrors and detectors. By choosing how to measure it at the very end of its journey, you can seemingly force it to have decided, billions of years ago, whether it traveled as a single particle or as a spread-out wave. Your observation in the present rewrites the history of the cosmos. This creates a deep entanglement between the mind and the cosmos, a modern version of the ancient mind-body problem. Where does the physical brain end and the conscious experience of reality begin? If our observations can collapse quantum probabilities, then the stable world we perceive might be a collective agreement, a consensus reality shaped by billions of observing minds. Could it be that certain physical laws only became fixed because conscious life eventually evolved to observe them? This is a staggering thought. The force of gravity or the speed of light might have remained fluid, mere suggestions, until a thinking species looked out at the stars and, in doing so, cemented those rules into permanence. It suggests that our journey to understand the cosmos is not separate from the cosmos understanding itself through us. This intimate connection between inner experience and outer reality is so fundamental that it echoes through our oldest stories. Long before telescopes or particle accelerators, human myths and legends may have been recording the echoes of these very cosmic anomalies, preserving the memory of a time when the rules were not yet set in stone. Our oldest stories whisper of a time when the sky itself was unstable. Cultures across the globe preserved tales of global floods, falling skies, and suns that behaved erratically, narratives that sound less like superstition and more like eyewitness accounts of a cosmos in turmoil. The Norse prophesied Ragnarök, a twilight of the gods where the world tree trembles and the sun is swallowed, only for a new green world to rise from the watery abyss. Hindu scriptures describe immense cycles of creation and dissolution, where the universe is breathed in and out by a divine presence, a rhythmic pattern of death and rebirth spanning billions of years. These are not merely metaphors for the seasons, but grand visions of cosmic resets, eerily similar to the phase transitions and vacuum decays of modern theoretical physics. Could these legends be a form of ancestral memory, a deep time record of moments when the rules of reality truly did falter? Experts like Carl Sagan argued that myth and science are two complementary human responses to the cosmos, and that oral traditions often encode precise astronomical knowledge. A sudden, brilliant new star appearing in the sky could be remembered as a god's fiery birth. Geological evidence adds a startling layer of credibility to these ancient accounts. Ice cores and sediment layers reveal periods of abrupt, catastrophic climate change, with temperatures plunging or soaring within a single human generation. Some scientists theorize these events could be linked to a nearby supernova's radiation, or even a subtle shift in Earth's rotational axis, a pole shift that would have made the stars appear to tumble from their fixed positions. If the very ground beneath your feet and the sky above your head were suddenly, violently different, would you not describe it as the gods rewriting the world? These stories challenge us to reconsider the stability of our own era. Are we living in a calm chapter between cosmic upheavals, our predictable physics merely the quiet after the storm? The tales our ancestors told around fires might be the most human record we have of the universe's capacity for self-reinvention, a poetic echo of the primordial chaos that forged the rules we now take for granted. This search for echoes of cosmic rule breaking now drives us to build new tools, instruments powerful enough to listen for the faint tremors of a reality rewriting itself in the present day. Scientists are now hunting for the cracks in reality with tools of unimaginable precision. Deep underground at CERN, the Large Hadron Collider smashes protons together at nearly the speed of light, recreating for a fleeting instant the searing energies of the primordial universe. Inside its 17-mile ring, detectors the size of cathedrals watch for the debris of these microscopic collisions, searching for new particles or forces that do not fit the established model. Physicist Lisa Randall and her colleagues scrutinized the data for any anomaly, a particle decaying at an unexpected rate or a flicker of energy that cannot be explained. Any such deviation could be the first clue that our current laws are an approximation, a low-energy shadow of a deeper, more complex truth. The discovery of the Higgs boson was a triumph, but it also confirmed that the standard model is incomplete. The hunt is now on for phenomena that point to a more fundamental layer of physics, one where the rules we know begin to bend and break. Meanwhile, on a different frontier, facilities like the LIGO Observatory listen for the faintest tremors in space-time. Their laser beams traveling down miles-long vacuum tubes can detect gravitational waves, ripples generated by cosmic cataclysms like colliding black holes. But scientists hope to hear something even more profound, the primordial echo of a cosmic phase transition. The violent shift from free quarks to confined protons in the early universe should have sent a thunderclap of gravitational waves across the cosmos. Detecting that specific hum would be like finding a fossil of the moment matter was forged, direct evidence of a past where the rules were different. This search extends to the heavens, where telescopes scan for the invisible signature of dark matter. We know it exists by its gravitational pull, but it does not interact with light or ordinary matter in any way we understand. The leading candidates are WIMP, weakly interacting massive particles that could be detected in ultra-sensitive underground labs as they occasionally bump into a nucleus. Yet decades of searching have come up empty, suggesting that dark matter may be something far stranger, a substance governed by its own hidden physics that operates outside our standard model. What if the next major discovery at a collider or observatory is not just a new particle, but a complete anomaly that our theories cannot digest? Such a finding would be more than a puzzle. It would be a revolution, forcing us to acknowledge that our cosmic rulebook is provisional. The technologies born from this quest, from quantum sensors to new materials, could reshape our world in ways we cannot yet foresee, proving that the most profound journey into the unknown begins by admitting that we may not yet understand the most basic rules of the game. The same cosmic rule breaking that forged the universe could one day forge our future. Imagine a civilization that graduates from merely understanding physics to actively engineering with it, using the very anomalies that once terrified theorists. This is the promise of a final theory, a unified understanding of reality that would hand us the universe's source code. Physicist Michio Kaku envisions a future where such knowledge unlocks technologies indistinguishable from magic. Warp drives, long confined to science fiction, could become a theoretical possibility by manipulating the fabric of space-time itself, creating a bubble of distorted gravity that carries a ship faster than light without breaking the local speed limit. The energy for such feats might not come from burning fuel, but from tapping into the vacuum of space itself. Remember that seething quantum foam with its unimaginable energy, the source of the vacuum catastrophe. If we could learn to stabilize a tiny region of space, or even harness the decay of a false vacuum, we would access a power source of literally cosmic proportions. The entire energy output of a star would pale in comparison to the potential locked within nothingness. Communication would be utterly transformed by quantum entanglement. While we cannot send information faster than light, entangled particles could create perfectly secure, instantaneous quantum networks. A message sent from Earth to Mars would arrive without any travel time, its security guaranteed by the fundamental laws of quantum mechanics. Any attempt to eavesdrop would disturb the delicate entangled state, immediately revealing the intrusion. We are already taking the first tentative steps toward this future in laboratories today. Researchers are designing metamaterials, artificial structures with properties not found in nature, that can bend light in seemingly impossible ways, creating rudimentary invisibility cloaks. These materials work by manipulating the symmetry of electromagnetic waves, a direct, albeit crude, application of the same principles that govern cosmic phase transitions. What if we could design a material that controls gravitational waves as easily as we control light? The engineering paradigms of tomorrow will not be based on steel and concrete, but on controlled symmetry breaking and quantum field manipulation. Consider a hypothetical device known as a vacuum stabilizer. By applying precisely tuned energy fields, it might be possible to nudge a small region of space into a more stable state, releasing a burst of usable energy as it drops into a lower energy level, much like the ball rolling down the hill in our cosmic symmetry break. This would not be combustion or nuclear fission, but a direct conversion of spacetime's latent structure into power. But with such godlike power comes profound responsibility. What are the ethical implications of a species that can tamper with the vacuum itself? A failed experiment could, in the most extreme theoretical scenario, trigger a catastrophic phase transition, a bubble of new physics expanding at light speed, rewriting the laws of reality and erasing our universe in its wake. The very act of observation that solidifies reality could one day be turned into a tool for its redesign. Are we, with our limited wisdom, ready to hold the blueprints for cosmic creation? This question leads us from the realm of physics into the deepest waters of philosophy and consequence. If reality's laws are temporary, then our own existence rests on shifting sand. This is the philosophical earthquake that follows the collapse of absolute physics, forcing us to question everything we thought was permanent. What does it mean to have free will if the chain of cause and effect is not a fundamental rule but a local custom, one that can be suspended inside a black hole or rewound in a time loop? The very notion of truth becomes unstable in a multiverse, where every possible version of events is playing out somewhere. Your greatest triumphs and deepest regrets are not unique, but are mirrored in countless parallel realities, each with its own slightly different history. Philosopher Thomas Kuhn described how science itself does not progress in a straight line, but through violent revolutions he called paradigm shifts. The comfortable, predictable cosmos of Newton was overthrown by the relative universe of Einstein, which was in turn unsettled by the probabilistic ghost world of quantum mechanics. Each time, the entire framework of understanding was torn down and rebuilt. We may be living on the brink of the next great shift, a moment when our current rulebook is recognized as just another provisional draft. This fluidity of reality gives new life to ancient philosophical puzzles. Solipsism, the idea that only one's own mind is sure to exist, seems less absurd if the external world is a quantum construct that requires observation to snap into focus. Simulation theory, the notion that we live in an advanced computational reality, becomes a plausible scenario if the laws of physics are just the operating code of a system that could be patched or rewritten. These are not just thought experiments for dorm rooms, but serious considerations in a cosmos that has demonstrably changed its own settings before. Consider the chilling concept of a Boltzmann brain. This thought experiment, stemming from thermodynamics, suggests that in a vast and eternal universe, a single, self-aware brain could spontaneously form from a random fluctuation in the quantum vacuum, complete with a full set of false memories and a sensory experience of a world that does not actually exist. You could be that brain, having just popped into existence a moment ago, with your entire life and all your knowledge merely an elaborate illusion. it is a stark reminder that our most cherished experiences could be utterly ephemeral. So how do we find purpose or meaning in such a transient cosmos? If the universe can forget its own rules, then our search for eternal truths may be the most fleeting thing of all. Perhaps meaning is not something we discover written into the fabric of reality, but something we actively create through our relationships, our curiosity, and our acts of compassion, even if they are just temporary patterns in a forgetful void. This realization carries profound ethical weight. If we are ever to advance to the point of manipulating the fundamental forces, we must ask not only if we can, but whether we should. The power to rewrite physics is the power to unmake and remake existence itself, and with it comes a responsibility that transcends any we have ever known. The power to probe the origins of the cosmos carries a responsibility of almost unimaginable scale, as we experiment with forces that could theoretically alter reality itself, from creating microscopic black holes in particle colliders to potentially disturbing the vacuum of space. We are forced to confront a new ethical frontier. The late Stephen Hawking repeatedly voiced concerns about such high-energy experiments, suggesting that what we might unleash could be far greater than what we intend to control. The core dilemma is this: does humanity's insatiable curiosity to understand the universe justify risks that, however small, could rewrite existence? These are not questions for physicists alone, but for all of us. We can adapt principles from bioethics, like the precautionary principle, which argues that if an action has a suspected risk of causing severe harm, the burden of proof falls on those taking the action to show it is safe. In cosmology, this translates to a demand for rigorous safety assessments before we conduct experiments that recreate conditions not seen since the first moments of the Big Bang. International scientific bodies have established regulations and review committees for projects like the Large Hadron Collider, which extensively studied the possibility of creating stable micro-black holes or strangelets that could convert ordinary matter into a new form. Their consensus was that such events were impossible or would decay harmlessly, but the debate itself highlights the profound stakes. Is it ethical to gamble with a 1 in a trillion chance if the consequence is the end of everything? This forces us to weigh the immense potential benefits of a final theory, which could unlock clean energy and technologies beyond our dreams, against the existential risk of a single, irreversible mistake. Your own sense of caution might be tingling right now. Where do we draw the line between reckless ambition and courageous discovery? Preparing for these mysteries requires more than just advanced physics. It demands a global conversation about our role as a species suddenly entrusted with cosmic tools. This journey of education begins not in a laboratory, but in our classrooms and public forums, equipping the next generation to approach the universe's deepest secrets with both wonder and profound humility. A classroom in the 2024 does not need a rocket ship to visit the edge of a black hole. Students wearing virtual reality headsets can watch with their own eyes as space-time warps into a funnel of distorted light, visualizing the very moment physics breaks down. This is the new frontier of education, where interactive simulations and thought experiments transform abstract cosmic anomalies into tangible, explorable worlds. Educators are building curricula that braid together history, philosophy, and cutting-edge science, creating a rich tapestry of understanding. In one lesson, a student might grapple with the philosophical implications of the multiverse before using a simple online tool to manipulate the fine structure constant and witness how a universe with slightly different rules would fail to form atoms. Scientists and communicators like Neil deGrasse Tyson champion this approach, arguing that the most complex ideas become intuitive when we replace rote memorization with a sense of wonder and direct engagement. National programs from NASA, extensive public outreach to university-led summer camps, are designed to dismantle the intimidation that often surrounds theoretical physics. They actively address common misconceptions, like the idea that a black hole is a giant vacuum cleaner in space, by letting students virtually drop a clock toward an event horizon and see for themselves how time appears to slow to a standstill. The core of this method is to encourage questions that have no easy answers. How would you explain gravity to an alien from a universe with 5 dimensions? What would a creature made of dark matter perceive as reality? By giving young minds the freedom to ask, we are not just teaching them science, we are training them to become the next cosmic explorers, comfortable with uncertainty and hungry for the next great mystery. This foundational curiosity naturally seeks new forms of expression, leading us beyond equations and into the realm where art and cosmos collide. Artists have long been the cartographers of the invisible, mapping territories where mathematics alone cannot tread. When physics describes a reality in flux, where rules can be rewritten and time can loop, creators with brushes and instruments step in to give these abstractions a face and a feeling. A painter might depict the quantum foam not as an equation, but as a seething, bubbling canvas where forms constantly dissolve and reassemble, a visual echo of the vacuum's hidden frenzy. Composers translate the concept of cosmic inflation into sound, building symphonies that begin with a single, sustained note before exploding into a chaotic, accelerating crescendo of strings and percussion, mimicking the universe's own violent birth. These works do not seek to explain, but to evoke, allowing us to feel the disorienting weight of a cosmos without fixed laws. This collaboration between science and art is more than metaphorical. Physicist Brian Greene has frequently worked with filmmakers and digital artists to create visualizations for string theory's hidden dimensions, transforming complex mathematical shapes into swirling, luminous sculptures that dance across a screen. In cinema, films that play with nonlinear time and causal loops are more than just entertainment. They are thought experiments in narrative form. When a character relives the same day, their frustration and confusion become a human-scale analogy for a closed time-like curve, a personal experience of a broken causal chain. Digital artists now use generative algorithms to create real-time simulations of the multiverse, where every click of a mouse causes a new universe to branch on the screen, a breathtakingly immediate representation of the many worlds interpretation. These artistic interpretations serve a profound purpose. They bridge the gap between intellectual understanding and emotional resonance. Staring at a painting of a fractured landscape where gravity operates in multiple directions at once can instill a deeper, more intuitive sense of spatial relativity than a textbook ever could. Listening to a musical piece composed around Heisenberg's uncertainty principle, with melodies that never quite resolve, can make you feel the inherent fuzziness of reality in your very bones. So, does this mean that art and science are two different languages describing the same truth? Perhaps they are complementary forces, one providing the data and the other the meaning, working in tandem to illuminate the full spectrum of our cosmic condition. This visceral encounter with a fluid reality through art inevitably leads us to a more personal question. How does the knowledge of such profound instability affect the human mind looking up at the stars? This constant confrontation with cosmic instability can unsettle the human mind at its very core. We are wired to seek patterns and predictable cause and effect, a mental framework that has ensured our survival for millennia. To then be told that the bedrock of reality is not just shifting sand, but a substance that might vanish entirely, can trigger a profound psychological dissonance. It is a confrontation with the sublime, a mixture of awe and terror that philosophers have described for centuries. The vast, orderly cosmos of Newton offered a kind of psychological comfort, a paternal universe governed by knowable laws. The chaotic, probabilistic, and forgetful cosmos of modern physics can feel like a form of abandonment, leaving us adrift in a sea of endless possibility and existential risk. This is not just an intellectual exercise, it is an emotional and spiritual challenge. The psychologist Carl Jung explored how archetypes of chaos and order are fundamental to the human psyche, representing a deep, unconscious struggle between the desire for stability and the terrifying thrill of the unknown. When our scientific models reveal a universe capable of radical self-reinvention, it resonates with these ancient, internal patterns. The cosmic dragon of chaos is no longer a myth, but a theoretical possibility lurking in the quantum vacuum or at the heart of a black hole. How do we cope with this knowledge without being paralyzed by anxiety? Many turn to mindfulness and grounding practices, focusing intently on the present moment and the tangible reality of a breath, a sensation, or a shared smile. These practices do not deny the cosmic scale of uncertainty, but they anchor the mind in the one reality we can directly experience, our immediate consciousness. Others find solace in community, joining online forums or local astronomy clubs where the overwhelming nature of these concepts can be shared and dissected. There are support groups, both formal and informal, for people whose fascination with cosmology borders on existential obsession, where members reassure each other that feeling small is not the same as feeling insignificant. The very act of seeking understanding becomes a coping mechanism, transforming dread into curiosity. So how do we maintain our mental balance in a cosmos that seems so capricious? Perhaps the answer lies not in finding permanent answers, but in building a resilience that can accommodate the mystery itself. This psychological need for stability, however, runs directly into a very practical world, one governed by budgets and balance sheets, raising the inevitable question of what price we are willing to pay for this unsettling knowledge. The search for cosmic truths carries a multi-billion-dollar price tag. Governments and private entities pour staggering sums into colossal machines and space-bound observatories, all to chase the ghost of a broken physical law. A single mission like the James Webb Space Telescope represents an investment of $10 billion, while the annual operating cost for a facility like the Large Hadron Collider runs into the hundreds of millions. These are not small sums, and they demand a justification that goes beyond pure curiosity. The funding for this fundamental research comes from a complex ecosystem of national science foundations, international consortia, and increasingly from private visionaries. Figures like Elon Musk and Yuri Milner fund projects aimed at uncovering the nature of reality, driven by a belief that our future survival may depend on understanding the universe's deepest operating principles. Astrophysicist Neil deGrasse Tyson is a leading voice in arguing for the long-term economic and technological return on this investment. He points out that the quest to probe cosmic anomalies has historically been a powerful engine for innovation. The entire Global Positioning System, GPS, is a direct spin-off from fundamental physics. Its astonishing accuracy depends entirely on corrections for both special and general relativity, accounting for how time flows slightly differently for satellites in orbit than for receivers on the ground. Without that investment in understanding Einstein's theories, our modern world of navigation and logistics would look utterly different. The development of the World Wide Web at CERN is another classic example, created not to study the cosmos, but to help physicists share their data, a tool that then reshaped human civilization. A rigorous cost-benefit analysis, however, must confront a difficult question. Is it responsible to spend billions searching for theoretical particles or gravitational waves when that same money could address immediate, pressing needs on Earth from poverty to disease? The counter-argument rests on the unpredictable nature of discovery. When scientists began studying quantum mechanics a century ago, they were not trying to invent the transistor or the laser. They were simply trying to understand the bizarre rules of the atomic world. That pure, curiosity-driven research ultimately gave us every modern electronic device and the entire field of digital communication. The economic value created by the transistor alone dwarfs the entire historical investment in quantum research. The next great discovery, perhaps hidden in the data from a gravitational wave observatory or a new space telescope, could unlock an energy source or a material that solves problems we cannot yet even conceive. This global endeavor also reveals fascinating cultural priorities. Different societies choose to fund this search in different ways, reflecting their unique values and their philosophical stance on humanity's place in the cosmos. Some nations view it as a national prestige project, a way to demonstrate technological prowess. Others frame it as a long-term investment in human knowledge, a collective insurance policy for our species' future. How does a culture that prioritizes immediate, tangible results weigh the value of a photograph of a black hole's shadow, an image that offers no practical application but fundamentally alters our perception of reality? The way a society answers that question tells us less about physics and more about its vision for the human spirit. This divergence in how we value the intangible mysteries of the cosmos is mirrored in the very different stories we have told about them throughout history. Ancient cultures did not need telescopes to perceive a cosmos in flux. For the Aboriginal peoples of Australia, reality itself was sung into existence during the Dreamtime, a foundational era when ancestral beings moved across the land, shaping mountains and rivers through their journeys. This was not a one-time creation event, but a continuous process where the physical world is maintained through ritual, story, and song. The landscape is alive with memory and lore, and a breakdown in this sacred order is not a scientific anomaly, but a spiritual rupture that requires ceremonial repair. Similarly, Taoist philosophy from China envisions a universe governed by the dynamic interplay of yin and yang, a perpetual dance of complementary opposites. A cosmic breakdown, a moment when physics fails, could be understood as a severe imbalance, a point where one principle so overwhelms the other that the entire system must recoil and reset itself to find a new harmony. The Tao Te Ching speaks of the way that cannot be named, a fundamental principle that precedes all laws and forms, echoing the physicist's singularity where known rules dissolve. The anthropologist Claude Lévi-Strauss argued that all human societies, from scientific to indigenous, create complex structures of myth and classification to make sense of the fundamental binaries of existence, especially the tension between chaos and order. A myth about a great flood or a falling sky is not a primitive misunderstanding. It is a culture's intellectual framework for processing the trauma of cosmic instability. The Mayan long count calendar, which famously fueled speculation about an end date in 2012, was not a prophecy of doom but a marker for the end of a great cycle and the beginning of the next. It encoded a deep understanding of cyclical time, where universes are periodically destroyed and reborn, much like the cosmological phase transitions of modern physics. In Buddhism, the concept of kalpas describes immense cycles of formation, stability, dissolution, and void, a cosmic rhythm of birth and death on a scale that dwarfs human history. A black hole's singularity, a point of infinite density, finds a parallel in the void state between cycles, a ground of all potential from which a new reality will spontaneously manifest. These are not merely different stories for the same scientific facts. They are different ways of knowing, of relating to the mystery of existence. When a culture performs a ritual to ensure the sun will rise again, they are not ignorant of astronomy. They are actively participating in the maintenance of cosmic order, reinforcing the relationship between humanity and the cosmos through symbolic action. So, can we blend this deep cultural wisdom with our scientific models to gain a richer understanding? Science gives us the equations for a quantum fluctuation, but myth gives us the language to grapple with its meaning. Science describes the mechanism of a false vacuum decay, but philosophy offers frameworks for contemplating the ethics of a universe that can be so fragile. This fusion of knowledge systems is already happening as scientists collaborate with indigenous elders to understand celestial events recorded in oral histories, or as philosophers of science draw on Eastern non-duality to interpret the observer effect in quantum mechanics. This collaborative search for truth is then filtered through a powerful modern lens, the storyteller of our age, the media, which holds immense power to shape how we all perceive these cosmic breakdowns. A black hole's gravitational ballet in Interstellar gave millions their first visceral understanding of time dilation. This is the power of popular media, translating the universe's most bizarre rule breaking into gripping human stories. Films like Contact explore the implications of wormhole travel, while series like Doctor Who turn paradoxes into plot devices, simplifying concepts that would otherwise remain trapped in textbooks. These narratives, though often exaggerated for drama, serve a crucial purpose. They raise public awareness and spark a foundational curiosity about how reality truly works. The involvement of actual physicists ensures these stories are grounded in genuine science. Kip Thorne's work as a scientific consultant on Interstellar not only shaped the film's stunning visual representation of a black hole, it also led to genuine scientific papers on the gravitational lensing of accretion disks. This collaboration between Hollywood and academia creates a feedback loop where artistic imagination inspires new questions for research, and scientific discovery, in turn, fuels new stories. We see common tropes emerge again and again. The Marvel Cinematic Universe constantly plays with the idea of parallel realities and branching timelines, presenting the multiverse as a chaotic web of what-if scenarios. While the science is stretched for spectacle, it introduces audiences to the profound notion that our timeline is not the only one. Novels like Philip Pullman's His Dark Materials build entire cosmologies around the concept of dark matter and interacting worlds, personifying abstract particles as magical, conscious dust. Video games allow us to play with broken physics directly, manipulating time in titles like Braid or navigating non-Euclidean spaces that defy all conventional geometry. But how accurate are these thrilling depictions? When you watch a character step through a portal into another dimension, consider what is being left out. The sheer energy required to warp space-time, the potential for instant disintegration, or the causal nightmares that would accompany any such journey are often glossed over for the sake of a clean narrative. This is not a flaw, it is a creative choice, but it is one worth questioning. Does the portrayal of a parallel universe as a simple mirror world help us understand the many worlds interpretation, or does it obscure the truly alien nature of quantum branching? These fictional explorations do more than just entertain. They act as a cultural testing ground for ideas that are still too new for our equations to fully capture. They prepare our minds for the shocking possibilities that science may one day confirm, making the incredible feel a little more familiar. This blending of art and science points toward a necessary future, one where storytellers and physicists work in even closer concert to map the uncharted territories of a reality whose rules are still being written. A physicist, a philosopher, and a digital artist walk into a lab, and it is not the start of a joke but the future of cosmic discovery. The immense puzzle of a universe that rewrites its own rules cannot be solved by one field alone. It demands a chorus of perspectives, a fusion of different ways of knowing. When cosmologists collaborate with computer scientists, they can build digital universes in silicon, running countless simulations to see which initial conditions and rule changes lead to a cosmos that looks like our own. These are not video games, but rigorous testing grounds for ideas about inflation, vacuum decay, and the nature of time itself. An engineer might design a more sensitive detector for a gravitational wave observatory, inspired by an artist's visualization of how space-time ripples. An ethicist works alongside the physicists at CERN, helping to frame the profound responsibilities that come with experiments that recreate primordial fire. The visionary physicist Freeman Dyson long championed this cross-pollination of ideas, arguing that the most revolutionary insights often bloom at the fuzzy boundaries between established disciplines. Look at the monumental achievement of the Event Horizon Telescope. It was not a single team in one country, but a global alliance of radio astronomers, computer scientists, and data analysts who collectively transformed the entire planet into a single, giant telescope to capture the first image of a black hole. Their success was built on a foundation of shared data, diverse expertise, and a common, almost impossible goal. At international conferences dedicated to the foundations of physics, you will now find sessions where string theorists debate with cognitive scientists, each group asking the same fundamental question from wildly different angles. What is the nature of reality, and how does our perception of it shape its rules? How can we dismantle the silos that have traditionally separated a poet from a physicist when both are, in their own language, describing the same sublime mystery? This collaborative spirit is the engine that will drive the next great leap, pushing our inquiries beyond the known and into the breathtaking possibilities of what might come next. The next great discoveries in physics will not come from a single telescope, but from a web of minds and machines spanning the globe. We are building the tools to watch a black hole's birth cry and to feel the tremors of the universe's first second. The Laser Interferometer Space Antenna, or LISA, is a planned mission that will float 3 spacecraft in a perfect triangle, millions of miles apart, using laser beams to listen for gravitational waves too low-pitched for any Earth-based detector to hear. It will catch the faint whispers of colliding supermassive black holes and perhaps the relic hum from the cosmic inflation itself, a direct recording of the universe's most violent growth spurt. On the theoretical front, the quest to heal the rift between gravity and the quantum world is pushing into wild new territories. String theory suggests that the fundamental ingredients of reality are not point-like particles, but tiny, vibrating loops of energy. Their different vibrations could give rise to every force and particle we see, all within a cosmos that has many more than the 3 spatial dimensions we experience. Imagine a universe where every particle is a distinct musical note played on an unimaginably small string. Loop quantum gravity, championed by thinkers like Lee Smolin, takes a different path. It proposes that space itself is not a smooth continuum, but is woven from a fabric of tiny, finite loops. This fabric would have a natural grain, a smallest possible unit of space, preventing the infinities that plague our current equations at the heart of a black hole or the Big Bang. Think of a digital photograph where a beautiful, smooth image is actually composed of countless tiny pixels. Reality itself might be pixelated, To test these breathtaking ideas, we may need to build probes of a kind we can barely conceive. What would an experiment to detect an extra dimension look like? One possibility involves searching for gravity leaking into these hidden dimensions, which would make it appear weaker at very small scales than our models predict. Artificial intelligence is becoming an essential partner in this search, sifting through mountains of data from particle colliders and telescopes to find the one in a billion anomaly that human eyes would miss. An AI might spot a particle decaying in a way that breaks the standard model, or a pattern in starlight that hints at a warp in the fabric of space-time. These are not distant dreams. Your own computer could soon contribute to this search through citizen science projects, where volunteers lend their devices processing power to help simulate universes or analyze cosmic signals. The next Einstein might not be working in a university lab, but could be a curious person like you, spotting a pattern that everyone else overlooked. How will you know when the next great rule break is discovered? It will not arrive with a thunderclap, but as a quiet, persistent anomaly in the data, a single note that does not fit the established symphony of physics, forcing us to listen to the universe in a whole new way. The search for cosmic rule breaking is no longer confined to elite institutions with billion-dollar budgets. An amateur astronomer in their backyard, a student with a laptop, anyone with curiosity can now join the hunt for anomalies that challenge our understanding of physics. Online platforms like Zooniverse connect millions of volunteers with real data from the world's most powerful telescopes, inviting them to scan the skies for the unexpected. You might be the first person to see a strange flicker from a distant galaxy, a signature of a star being torn apart by a hidden black hole, or a distorted arc of light caused by the gravitational lensing of dark matter. This is citizen science, a global movement that leverages the power of human pattern recognition, something computers still struggle with, to sift through the cosmic haystack for the needle that breaks all the rules. Planetary scientist Carolyn Porcu champions this collaborative approach, noting that a fresh pair of eyes, untrained by academic assumptions, can sometimes spot the subtle oddity that a seasoned expert might overlook. It was volunteers who helped classify millions of galaxies for the Galaxy Zoo project, leading to the discovery of entirely new types of celestial structures. Enthusiasts sifting through data from the Kepler Space Telescope have identified potential exoplanets that automated algorithms missed, worlds orbiting in bizarre configurations that test our models of solar system formation. The tools are more accessible than ever. You can download software to analyze the light curves of variable stars from your home computer, or join a project searching for the elusive planet 9 in the outer solar system by meticulously scanning archival images. Other initiatives crowdsource theoretical ideas, inviting the public to help develop new models to explain the vacuum catastrophe or propose experiments to test the nature of dark matter. When thousands of minds from different backgrounds and cultures focus on a single cosmic puzzle, the collective intelligence can crack problems that have stumped specialists for decades. So where do you fit into this grand exploration? You do not need a PhD to contribute to the greatest story ever told. Your curiosity and a little time are the only requirements. What hidden cosmic secret is waiting for your eyes to find it? This journey through a universe of forgotten rules ultimately leads back to a single, personal reflection. We have traveled from the fiery forge of the Big Bang to the silent, seething vacuum, from the shattered causality of black holes to the branching paths of the multiverse. We have seen that the constants we rely on might be transient and the laws we cherish temporary. This knowledge can feel overwhelming, like learning the ground beneath your feet is not solid rock but a thin crust over an endless abyss. Yet this very instability is the source of all possibility. It is the reason stars could ignite, planets could form, and life could evolve to gaze back at the cosmos with wonder. The universe's capacity for self-reinvention is not a flaw, but its most profound feature. Our own existence is living proof that from chaos, complexity can emerge. From the ashes of broken physics, new rules can crystallize, allowing for beauty, consciousness, and the relentless pursuit of understanding. We are not just bystanders in this cosmic drama. We are the universe becoming aware of itself, questioning its own origins and imagining its ultimate fate. Our search for meaning, our drive to connect, and our acts of creation are the universe's way of remembering what it truly is. This cosmic instability is not just a distant theory, but a perspective you can carry into your own life. Understanding that the universe's rules are fluid can transform how you face daily challenges, replacing a need for absolute control with a resilient curiosity. When a personal plan falls apart or a long-held belief is challenged, it no longer has to feel like a failure of the cosmos, but rather a small echo of its inherent capacity for change. Insights from mindfulness practices show that accepting this fundamental flux rather than fighting it can significantly reduce anxiety. The struggle for permanence in an impermanent world is a primary source of stress. By internalizing that even the laws of physics are provisional, you can learn to meet uncertainty not with fear, but with a sense of exploration. Practical steps can make this abstract idea tangible. You might start a journal where you ponder cosmic questions alongside your own. How does the fact that atoms in your hand were forged in a star's death influence your sense of connection? Discussing these themes with friends or in community groups can open surprising conversations, shifting focus from daily grievances to a shared wonder about our place in this strange and evolving reality. How has this exploration of forgotten rules and rewritten reality changed your own perspective? Does the knowledge that our existence is a beautiful, temporary pattern in a forgetful void make it feel more precious or more fragile? This personal reflection is the final piece, preparing us to see the entire journey not as a collection of facts, but as a single, unfolding story about the nature of everything. Our journey through the edge of reality reveals a cosmos that thrives on transformation, not rigid commands. We have witnessed the universe at its most vulnerable, from the singularity where all laws dissolve to the quantum void where particles defy cause and effect. The profound insight is that cosmic order is not a given but a temporary and fragile state, repeatedly shattered and remade in moments of profound breakdown. Each collapse, from the inflationary burst to the breaking of fundamental symmetries, was not an end but a necessary renewal, a creative act that forged the stable conditions we now call home. This means our own understanding must remain fluid, always ready to adapt when the next anomaly in the data forces us to rewrite the textbooks. Navigating these endless mysteries requires our two most human tools: boundless curiosity and open collaboration. It is through sharing questions across cultures and disciplines that we map the uncharted territory of existence itself. Albert Einstein perfectly captured this spirit when he reflected that the most beautiful thing we can experience is the mysterious. It is the source of all true art and science. Let that sense of wonder be your guide. We would love to hear which cosmic rewrite fascinated you the most, so share your thoughts in the comments below. If you are ready to continue exploring the wonders of the cosmos, subscribe for more deep dives